All right, here's 11.1. We'll do it all in a single day. That hasn't been very common for us lately, but here we can. This is not, it's basically an excerpt from the book that I think is worth going back to read because it kind of summarizes chapter 11 pretty well. I'm not going to read it through now, but I kind of highlighted the big ideas. That in chapter 11 we move to this new set of procedures called chi-squared, and what they do is they allow us to do tests on data that's categorical. Okay, way back when we had looked at how data, this goes like way back to like summer homework, that there's two types of data, numerical and categorical. Everything that we'd been doing with tests and confidence intervals was numerical data. As far as doing any kind of test to make a conclusion about a population, we haven't done anything with categorical data, and now we do. And the type of tests that we use are called chi-squared. So this kind of gives you an outline of how it works. You'll still have HO and HA. You'll see it with the null hypothesis. It always follows, saying that how the data is spread out over the categories, that it does fit a specific pattern that we're looking for, and HA will say that it doesn't. Okay, but you'll still have HO and HA. And then the test really revolves around counts, observed counts and expected counts. Okay, and now in the examples we look at, we'll dive into this stuff a lot more, but these are terms that you should definitely know, particularly the counts, because those come up a lot in the test. First thing, there's the name, chi-square. There's the symbol for it, by the way. And one thing right off the bat, CHI, chi-squared. Don't call it chi-squared. Don't call it chi-squared. It's chi-squared. Okay? It's okay if you do call it those things, but I'm not going to be, thrilled about it, but I'll get over it. So the test revolves around calculating a chi-squared test statistic, and here's how it's done. Okay, so when it says observe, you have to have all these observed counts, and typically you calculate these expected counts. So it shows over here the distribution, and notice with chi-squared, it's kind of distinctly non-normal, and you'll see when we talk about conditions that there is no normal condition. Okay, because a chi-squared distribution isn't. It's skewed to the right. Okay. The degrees of freedom is described right here. It takes on a little bit different meaning. It's now the number of categories you have minus 1. Number of categories minus 1. Okay, and you can see the distribution seems to take on less and less of a right skew the more categories you have. Okay. A couple other things before we dive into some 4 steps. Kind of some warnings. Make sure that when you're doing a chi-squared test, you're always working with counts. Okay, to try to do them as proportions, that comes up a lot. It will be a disaster. You will not get to the same p-value. You won't get the same chi-squared value. Heavy emphasis on counts, right? You need to use counts. One of the conditions changes. Okay, random is still important. That always is. But condition number 2 is no longer normal, which, if you think about it, makes sense. We just talked on the other slide that chi-squared is a distribution that's right skewed. So why would we verify that it's normal when it's not? we call it the large numbers condition, and it is all about the expected counts. Those have to be greater than or equal to 5. Okay, so every single category, when we get our expected counts, they have to be at least 5. There's a couple different ways you could word HO and HA. I'm not a fan of this way. I'm a big fan of this way. To just say it in a sentence. Obviously, you need to have the context, right? That's kind of a thing for us all the time, that we like descriptions in context. And obviously I'll show you a couple examples. But HO will say that kind of basically that the observed counts that we have matches the expected. And HA is basically going to say that the observed and expected aren't the same. That there's some, it doesn't specify at all as to what the distribution is. Okay? All right, so here is our first set of data. It comes from a past census. That was from that census, we have the percentage of age categories that have a landline phone, which has become increasingly less common over the years. Okay? What we want to see here is if the age distribution, and excuse me, the data from the census is the age distribution. Okay? What we got from a sample was the number of individuals that said yes, that they have a landline phone. So to look ahead a little bit, when we get to HO, it would say that the distribution of individuals that have a landline phone is the same as their overall distribution to the population. That's more or less what we're saying here. Okay? So the first thing I have to do is to give expected counts. I'm going to calculate these, so the expectation will typically be that you don't need to. This is really just to have in your notes, because it's good to see how they're done. So I've got 50s and I've got 60s. Okay? So for our 20s, we have a sample of 1,048. Okay? And multiply that by the proportion that, according to the census, that people in their 20s accounted for 19.1% of the population. Okay? So here's my expected, and there's my observed. Okay, eventually when I get to calculating chi-squared, I'm going to be comparing those two. And it looks like from there that for people in their 20s, we would expect, if these two distributions matched, to see the same numbers. Okay? But it looks like, for the observed count for who actually had a landline, it seems low, right? It's less than what we would expect if it matched the population distribution. Okay? There's the expected count for 30s. Here is 40s. And this should have said 60 plus. right? So these, could be, I'm not going to write them all again up here, but like 225 would get compared to 186. So for each category that we now have an observed count that was actually, collected in terms of data, and we have this expected, okay? And again, the test is going to really be a comparison of these two. Do they seem like that they would be the same, or not so much? Okay, and again, what we're checking is the distribution of ages and homes that have a landline phone to see if they are the same or not. So this has most of the test written out. Let's start with HO and HA. It says the distributions who answer landline telephone surveys. That's, technically what it means, right? That they answered a landline. Or not exactly if they have a landline phone, but if they answered a landline survey. But that distribution is the same as the age distribution of all U.S. residents. HA says that it's not. Okay? Now, by the way, I haven't gotten into this at all because it won't really be relevant until 11.2. There are 3 types of chi-squared tests. This is called a goodness of fit. Okay? It only has one category, not multiple. But that's really a question for another day. Okay? For now, this is the only one that we'll cover. So, in anything in 11.1, you would just call it a goodness of fit. The data came from a random sample of 1,048 U.S. residents. There I listed off all the expected counts. Okay? Notice they're all at least 5. Don't call that the normal. That would be our large numbers. For chi-squared, I'm going to show the first 2. There's observed minus expected squared over expected. That was for people in their 20s. Okay? There would be 5 contributions total. I'm going to show 2, and that the pattern will continue. I'm also going to show the 30s. The observed for who answered the landline survey was 186, but if it had matched the A's distribution, we would have expected 225, roughly. Chi-squared would come from the calculator, right? You might, even though I haven't posted the tutorial for it yet, you could probably figure it out. It's under, you'll see the chi-squared symbol with GOF for goodness of fit. So our chi-squared kind of replaces our test statistic. We still have a p-value, which the test will give you. And you will see this relationship that large chi-squared values mean small p-values. Okay? Now if you think about it and you go chunk by chunk, right, because there would be 5 contributions to this chi-squared value. If the observed and the expected are really, really different, you're going to get a big chi-squared value. Okay? Which, that seems consistent with HA. That these 2 distributions are not the same, and of course that's the exact direction that we go. The p-value is less than 0.05. We reject HO, just like always. We'd say we have convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents. Okay, so it's, again, it's not that they didn't have a landline, it's that who would answer the landline to participate in the survey. Okay? That's what the sample of 1,048 really was just saying, hey, somebody answered, all we need is your age, right? And that was the age breakdown of who answered, okay? So basically, in terms of the age breakdown, you would get from this that a landline survey, may not give you a great age breakdown because it didn't seem consistent with the census. Okay, that those were different. Notice with this goodness of fit, it didn't get into how. Okay, it didn't get into how they're different. Now you can kind of look at the data and sort of figure it out, right? It looks like the folks in their 20s and 30s were underrepresented because they didn't answer as much, whereas people in their 60s were overrepresented. They were answering at a, there was more of them that were answering than you would expect according to the census. All right, we'll do one more. This one's a little quicker. In a book called Outliers, Malcolm Gladwell suggests that for certain sports, the odds that you would go on to play that sport professionally could be related to your age. And he lays out this theory based on based on your birthday, that dictates what youth program you would get into, right? And if your birthday is earlier in the year, you're older relative to who you're playing against, and you could therefore be more competitive, get more playing time, and have a better chance to develop, this kind of thing. Okay. First thing we got to look for here is observed counts. He randomly selected 80 NHL players. 32, 20, 16, and 20. Because he split up the year into 4 quarters, 1, 2, 3, and 4. Now here the expected is a little bit tricky, but what we're looking to see is if those birthdays are evenly distributed throughout the year. In other words, if you had an NHL player, they would be equally likely to be born in all 4 quarters. Okay, so once you have this, that's really what you got to start with to make sure that you're good to get your observed and your expected counts. Because once we have those, we're off and running. HO would say that the birthdays of NHL players are equally likely to occur throughout the whole year. Okay, think of the observed and expected counts matching. HA just says the opposite, that they don't match or that they're not the same. They're not equally likely. Chi-squared goodness of fit at alpha 0.05. Data came from a random sample of n equals 80 NHL players. Large numbers, all the expected counts are the same, and yes, 20 is greater than or equal to 5. I'm just going to write out all of them here just because this one's not that bad to do. There's the contribution for quarter number 1. Take a look at this. Right? That's a good one to highlight because we had talked in the previous example that large chi-squared values are evidence against HO. In other words, that will be consistent with a small p-value. Look what happens for a category if the observed and the expected match. You get a contribution of 0. Right? So if our observed and expected matched exactly, you would get a chi-squared value that's 0, okay? Which would be really, really consistent with what HO says, that the two distributions are the same. Quarter number 3, again, we see a somewhat significant difference there and one that's even more dramatic here in that'd be 11.2. Again, that might seem like a little bit of a mystery, but we'll get to the calculator feature. We had 4 categories here, so our degrees of freedom is just 3. But again, our p-value is less than 0.05, so we reject HO. And then we're convinced of what HA says, that the birthdays of NHL players are not equally likely to occur in each quarter throughout the year. If you get something like this, which is called follow-up analysis, you can get the contributions from the calculator, but if I broke it down, for that chi-squared value, we kind of talked about how each quarter was not appearing like it was contributing to the chi-squared value equally. Quarter number 1, which is January, February, and March, they had a lot higher observed. So when you break down the numbers, 7.2 of the 11.2 came from the first quarter. That was the biggest impact. Quarter number 2 didn't do anything. They didn't contribute a thing. Quarter number 3, sort of, not really. And then quarter number 4. So really the vast majority of that chi-squared value was that the observed count for first quarter was higher. The observed count for fourth quarter was a lot lower. Okay. That's, so, I mean, kind of the point of follow-up analysis is, notice here that we're kind of getting into Gladwell's theory as far as if the data is consistent. But notice in the conclusion of the goodness of fit test, we didn't address any of this. We just said the birthdays of NHL players are not equally likely, right? We said nothing about how. Follow-up analysis will start to get into a little bit of the how are they different. And in this case, it does seem consistent with Gladwell's theory from his book.